Okay, so we're going to talk a little bit about a very experimental project we did at the museum the Museum of Natural History in New York, to put constrained transport in the pencil code. This is stuff we did with Jason Marone and Mordecai McLowe. Is there a pointer too?
Yes.
So, obviously the first question that needs to be asked is why would we do this? Why would we add a new magnetic module? There's sort of three reasons. One, of course, is that solving for B allows for simpler initial conditions in certain cases, right? If you're solving for B, sometimes calculating the initial condition for B is easier than calculating the initial condition for A. It avoids the need for a second derivative in the evolution equations. Although, as obviously the pencil's success showed, this isn't really a very big deal. Although this is actually the reason, one of the main reasons why CT was introduced in the first place. If you go and read the Evans and Hawley paper, they were concerned that doing this formally lowers the order of the scheme by one to take a second derivative, and so that seemed like a bad idea. It may help in magnetic shocks, which Anders and I have had some trouble with in the pencil code, but that needs to be seen. But the real reason that we actually did it was just to see if it would actually work in a time-centered, non-conservative, high-order finite difference code. So essentially, people have sort of, for years, struggled. This is kind of obvious. The induction equation. There's this constraint we have to do. This is the div b equals 0, which analytically is always true because the curl of anything will not have a divergence. But numerically, we all know this doesn't actually happen all the time. And so there are a lot of methods to deal with this problem, right? You can use vector potential, which is what the pencil code does. You can project, you can transform into Fourier space. If you're in a spectral code, this is the obvious way to do it. And you just multiply k dot b hat and transform, then, take that out, set that to 0, transform back. The 8-wave solver at vex div.b, this works very well if you have open boundary conditions, solar wind type things. You just advect the divergence away. This is non-conservative though, so it doesn't work very well with these shock capturing Goodenough methods. The divergence diffusion, you can just diffuse, you can add an extra term that hits div b with some huge amount of diffusion and get rid of it that way. Or you can construct the induction equation to avoid div.b for all time to machine precision for a given discretization. So you have to define what div.b actually means in any finite difference scheme, right? So we're just going to refer to this constrained transport, meaning anything that's designed to do this by construction rather than doing something else, adding an extra term to the MHD equations or anything else like that. So just briefly, the original Evans and Hawley paper, which I forgot to put the date on, I think is 1988, uses a staggered grid. This is sort of the standard way to do it. You define vectors at the faces, you define scalars in the center, and you define the EMF at the corners. And then if you sort of construct this in your head, you see that it's quite trivial. It'll always be 0 because you'll add together all 4 corners when you calculate div b. And so it's 0. Stone and Irwin put it into Zeus, and so of course it simply proliferated widely from there. This has been updated in 95 to add a method of characteristics for upwinding along Alfvén characteristics, which helps for many problems, but in some such studies of MHD turbulence where you have magnetosonic and other wave modes rattling around, the upwinding along the Alfvén characteristic adds errors, which is how Jason got into this whole business of improving or changing constrained transport in first place. I added this last night. I'm not actually sure if the Nordland stagger code uses CT, although I presume it does since it has a staggered grid for B, and I can't think of any other reason why that would be so. So this proves that it can be done with high order, although it became more widely shown by a paper with Landrillo and Delzana in 2000, where they added a greater than second order CT method and wrote a paper about it. It's a very complicated paper, and I don't actually know if anyone has implemented this scheme at all. And then the sort of grand unification of all topics related to constrained transport was taught in 2000, where he took 7 different methods, pretty much everything I put up there, and put them into his massively configurable versatile advection code and tested them all on a whole bunch of different things. And there he showed, in fact, that CT does not require a staggered grid at all. You can formulate it using only centered derivatives. And so we set out to see if this would work for high order things. Because what this does is he coupled this to a Goodenough scheme. Well, actually, he coupled it to like 4 different Goodenough schemes, all with 7 different methods of div-D cleaning in a grand fashion. But the question is, if you don't have a conservative flux that you put in, will it still work? And so that's what we did. And so how do we add it? We difference E, which we define thusly, standard. I left out the muse, and then we difference this way. And everything is defined in cell centers, including the electric field, in our first thing. So CD, if you're familiar with the top paper, the centered difference constrained transport algorithm. What does this entail? Well, this figure looks really terrible, but there it is. So we calculate currents, so we add a magnetic CT module. It's much shorter than magnetic because it doesn't do anything. I cut out everything I didn't know what it was or didn't think would work. And so actually it's still not that small, strangely enough. But a lot of this is stuff that still doesn't actually need to be in there. This is just stuff because I took every public module that needed to be in there, so I didn't need to modify anything else. And so I just took them and took out all the content. So I made it like the no module. Anyway, we add E and J as communicated auxiliaries, which makes life very nice. It was easy to add them. So E is the EMF and J is the current. We now need J because we have to difference it, so we can't use it as a pencil anymore. So that's why it had to go in here. And this is actually PDE. I guess this is impossible to see. It looks much better on the screen. But we call cal currents in between this radiation transfer stuff and before the test field. And then this is the main PDE loop starting here. So each time step we calculate the E. The E field is the real important one. We calculate that and then go to, the DAADT routine is down here somewhere. So this is calculated first.
What do you J for? Why do you need to restore J?
That's a good question. Well, we use J to calculate the current. The resistivity. And so we need it. Do we need it everywhere on the grid?
Just get that
it's possible that I overstated this. I don't know. When I did this, which I should also mention that I did all of this 9 months ago, and I just redid it this weekend for the talk, so I probably have forgotten a lot of things. It's entirely possible that J doesn't actually need to be in there as an auxiliary at all. But anyway, we'll see in a second.
I like that. I have to say, I like the communicated auxiliaries you use, because that's another one of those things that when I implemented it, I was told was stupid.
No, it's fantastic. It's great. I've made excessive use of it.
No, it was useful with shortcode.
One question. In order to get d by dt, you calculate the curl of E or what?
Yes.
And J in turn is calculated as the curl of B.
That's right.
So does this mean that the diffusion term is basically the curl of a curl, evaluated twice in sequence?
I think that's right.
So that means for derivatives that, for example, a double X derivative, for example, is evaluated twice. That means the stencil is twice as long. Instead of 6, it actually goes over into 12 zones. Plus minus 6, that is, instead of plus minus 3. The other thing is, at the Nyquist frequency, the discretization error of the first derivative is infinite at the Nyquist frequency.
Okay.
Yeah. And so that doesn't become any better by taking another derivative. Whereas if you take a second derivative once, the error is a finite value is maybe 50% or could only be 20% or 30%. Now, because the diffusion term is of course extremely important for the Nyquist frequency, because that's where you want to get rid of the biggest, and if this doesn't work at all, then the diffusion term is useless. So you need to have a diffusion term, which actually works at the Nyquist frequency.
Right. That actually may come back as an issue that haunts this code, which is namely that the diffusion doesn't work.
Yeah. Okay.
That's why it has to have J as a communicated auxiliary.
No. It's a problem of evaluating the first derivative twice.
No, you mentioned 2 problems.
No.
You mentioned one that the stencil got too big, and the other that you shouldn't take a first derivative twice, you should take a second derivative once.
Yeah, but
the first issue, the stencil one, is
but that's not important. Yeah, I agree. But that's less important.
Yes,
it's related, of course. The important problem is really that you.
It's actually just that.
Yeah, that may in fact be. Yes. So obviously there are a lot of limitations. It's slower. It's not parallelized, and there's nothing at all. It's basically just does this work? Yes, no.
What do you mean? When it's not parallel, what do you need to communicate those theories?
In case I wanted to parallelize. It needed a place to go, and it needed to have boundary conditions set on it. Oh, I don't know. It's just not done yet. I do.
But what would you have to do?
Test it. I mean,
Test it, okay, I see, but I think it should already work. I mean,
one of my
the entire concept of communicator solution boundary, so it's already tested and it should work. So.
It depends if those things are really just calculated auxiliaries or look. Yeah, I can see a possible issue.
Yeah, what I mean by this is I've never tried. So usually it's best to say that it's not done if you've never even looked at it, right? But you're right. So in terms of the first test is just to test a 1D Alfvén wave. Now obviously this doesn't test div B at all because it's always zero identically. But it does test whether or not you're actually having a magnetic algorithm that works, because otherwise this wouldn't work at all. And as you can see here from this sort of very simpleton plot, we did 10 Alfvén crossing times in constrained transport and vector potential, and you overplot the U here and the B here. The pluses are the initial condition, and I don't even know what that symbol is. IDL PSIN number 2 is the thing. So you can see that the algorithm works, at least non-trivially. So another thing is then, okay, let's test MHD turbulence. And so what we do here is this is the BRMS from the helical MHD turbulence sample, run with constrained transport and the vector potential to T equals 50. And you can see that the RMS field is pretty much exactly the same. The max of the div B goes up, you can see here, and starts saturating. Hopefully it's saturating when the field is saturating. Now, one of the things, of course, is you can ask yourself, well, 0.01 is very large, and there's a lot of debate on this. First of all, it's possible that we could make this smaller, although usually the thing is you never know what max the div B should be, because it should be 0. The question is, what are the things you don't know the answer for? How badly is div B affecting the solution you're looking for? I admit this is still too high. And I think there's a reason for that, and I think it's also connected to this issue of the J. So diffusion in multi-Bs is problematic. And this could be because of the way I did it. I did it the simplest possible way, which is just curl B, take J, curl J. This is in fact taking the first derivative twice rather than the second derivative. And there's no reason why it has to be done the way I did it. It's just, I was trying to formulate it in the most general analytic way, which obviously is, if that were possible, then there'd be no need for doing constrained transport in the first place. And this is not very well constrained. So one of the things that's possible is we could interpolate the position, essentially use a staggering of the electric field without actually you don't even make a staggered grid. We can just calculate a flux across the surface and difference that. And that was one of the things I was hoping to do before this talk, but didn't get a chance to, since the train ride wasn't long enough. So that's sort of the next things. And then of course, so we can do this. There's two different ways to interpolate. You can spatially interpolate E, which is what I just mentioned. This is this flux center difference, so you don't actually need another grid. You could even do a high order interpolation of that electric field across, rather than just a second order interpolation. In other words, calculating the flux. So if we have this cell here, we define all of our variables here, and then we can construct some flux of Y and some flux of X, which we then is interpolated between these two and these two in the simplest possible scheme, and that gives us here, and then we difference that around there. So that's a possibility. The other possibility is to temporally interpolate E, which is a little more complicated. This is this field center difference formalism, in which you take the electric field from two different half-time steps and center it in time, and use that at the cell center. What's that?
That CD, that's what is done in what is done in JAS code, no?
In the what?
In the JAS code.
Yes.
I use that CD, yeah.
I think that's right.
Yeah.
So either one can be used. Flux CD is easier because you don't need to hold something in a half time, which is a little difficult with the RK3s, because then you have several points you could possibly interpolate from. And then the obvious, a much better test to do this is the circularly polarized nonlinear Alfvén wave. So you know, if you take an Alfvén wave and you circularly polarize it, it becomes an exact nonlinear solution. So you can give it an arbitrarily high amplitude and it will not distort, it will stay exactly. And so it's pretty easy, well, to implement, except it's much more complicated than a standard Alfvén wave, because you also want to put it at you want to propagate it at an angle, oblique angle to the grid, so that you're actually testing, and none of the fluxes are actually equal. This makes it a truly 2D test. And so I implemented this in the vector potential formalism, but I haven't gotten it to work yet, and I'm not actually sure why not. I should also mention that one thing that will always be a problem with constrained transport in the pencil coder, and any constrained transport code, and that's often overlooked, is that constrained transport only constrains div B to whatever it was when you started. So you have to have a very low div B in your initial condition numerically to the order of the scheme you're using. Otherwise, you simply sit around with whatever div B is on that grid, and it will happily keep it there. And that could corrupt the solution. So if you have any complex initial condition at all, you have to essentially clean it up somehow. And with an initial condition, that sounds easy because you could do the best possible thing. You could spectrally clean it, and it doesn't matter how much time it takes to do it. You can only do it once. Except for the fact that it has to be div B to the exact order of the scheme. You're going to then step it through time.
I had this problem before when I was also using Zeus for a short while.
Yep.
And that helped a lot to, if you have an initial condition where numerically there's a strong div B component, then it did help a lot to split off the initial condition from the B field, or subtract the initial condition from the B field and only evolve the difference. So you write B equal B prime plus B naught, and then B naught is constant, and you only evolve B prime, and then you write the equation when you impose analytically div B, you use analytically that div B should be 0, although it's in fact not.
Sure.
So that was kind of good.
Mm-hmm. Yeah, because that removes the, well, it will definitely keep exactly what we had at the beginning there.
But that doesn't even, that doesn't even have anything to do necessarily with advancing B as opposed to A. You can do it anyway.
Yeah.
So you can do the same trick also when advancing A.
B, yes.
Yeah.
Which is what you did.
This is true. But it also helps with B equals 0.
Yeah.
So, anyway, I didn't have a whole lot to say about this because we haven't really done a whole lot. But it is sort of interesting that you can formulate this way, and it seems like we can control things to the degree that some simulations will actually look the same, regardless of the A or B in 3D. The ones that tend to get really bad are the ones that require a lot of diffusion. The more diffusion you require, the worse it becomes, and there's a lot of checkerboarding instability that jumps out. And I think you may have found the exact reason why that is. Which maybe is the way I've done the A to J and the derivatives that I've used in order to do it. So that's just sort of one little weird branch of things that we've done that, if developed, and might be kind of interesting. And it would be especially interesting to see if it would help with these magnetic shocks, because that's a definite possibility when you cross this discontinuity.
So why would it help with the shocks?
Well,
because then you can accurately diffuse B.
that's part of it, right? You can diffuse B directly.
Instead of diffusing A.
A.
Why some of the diffusion might not make any difference.
That's right. That's exactly right. So,
Okay.
essentially it.
Thanks very much then. Well, let me first